So you guys have been working on some absolute dating challenges, and you'll remember from our song last week, relative shows order, but absolute is exact. And so, like, to me, it's pretty incredible. Well, let me back up. To me, it makes total sense that we have older rock layers on the bottom and then new ones get added on top. Like, to me, that's not like this crazy scientific notion. But the idea that scientists figured out now over 100 years ago how to count radioactive isotopes or radioactive forms of different elements and figure out how much is left and compare it to how much that should be, almost like a clock or a stopwatch, to find the exact age of a rock or fossil. To me, that's honestly pretty mind-blowing. So you've been working on challenges today about how to find the exact or absolute age of a rock or fossil. And so our first challenge was actually a graphing challenge, and the numbers that you were to graph started to get crazy small, right? So what we started to do is, if we went all the way through 10 half-lives, how much of the parent isotope would be remaining? Now, I know this is kind of weird language. The parent isotope is like what you start with. So with carbon-14 dating, the parent isotope means carbon-14. So after one half-life, only 50% of carbon-14 would be left, then 25%, then 12.5%, then 6.25. So finish my thought in your head. What we're noticing is the percent keeps getting cut in half, right? And then after the fifth half-life, only about 3% left. And it doesn't matter to me too much how far you went in terms of rounding at your decimal. You can see I really just took what popped up on my calculator this whole time. And so as we get to the seventh half-life and beyond, when we keep cutting it in half, we have even less than 1% left. Okay, so then the question is, how does this look on a graph? And it got pretty tricky to actually graph this towards the end, but your curve should look something just like this. Okay, so as we look, we can see again the first half-life, 50% of the parent isotope. That would also mean like the carbon-14 in the case of our flipping of the chips. Then 25%, 12.5%, 6.25%, and then it got basically close to zero. And eventually we know that it will run out. So now you had some questions that went with this. So do you think that a rock or fossil, that the percent of the parent isotope remaining, parent isotope again just means the original unstable radioactive form of the element, do we think that it always falls on one from the chart? And the answer is no. Now let me explain what I mean better by that. It's saying this: when scientists find a fossil, do you think it's always at exactly 50% or exactly 25 or exactly 12.5% or exactly 6.25%? And the chances are no. There's a much greater probability that it's falling in between one of those. So now it leads us to this. Can a scientist still figure out the exact absolute age of a rock or fossil if it doesn't fall in an exact percent? And the answer is yes. And so how are we to do that? Okay, so if you look now at this, let's say a fossil has 4.5% of its original carbon-14 remaining. That's how much is left, 4.5%. So if I come back to my chart, or I really could have gone to the graph, but 4.5%, okay, well, if there was 6.25% remaining, it would be 4 half-lives. 3.125, that would be 5 half-lives. So we see that that number falls in between the 4 and the 5, making this, here we go, our only answer that even makes sense. It would be about 4.5 half-lives. So now remembering each half-life is 5,730 years, what would be the absolute age of that fossil? The math isn't really terribly tricky at that point. You're taking 4.5 times 5,730, because each half-life is that long, and you get an absolute age of 25,785. So the whole point with these last two questions, it doesn't always fall exactly on a perfect whole number half-life, which is okay because you can still use multiplication to find the exact or absolute age. Okay, now the next one, the next and final challenge on this assignment, and I'm sorry that turned out just a touch blurry, but this is a diagram interpretation. And so this should remind you more of what we did actually with relative dating when you first look at it. Like, we can put these rock layers in order based on relative dating. But you notice there's this little chart over here. And it shows you that carbon-14 is not the only radioactive unstable element that rocks and fossils would have. There's also one, and there's more than even this, but the three we're focusing on, uranium-235 and potassium-40, they are also radioactive isotopes that scientists can use this same method with. By the same method, I mean they can use radiometric dating. They can be like, oh, how much of that is left compared to what there should have been, and figure out the absolute exact age. Okay, so the first set of questions here, first question I should say, says, scientists found a bone in layer Z. So the first thing you have to do is look at layer Z, and you see it up here on top. And this bone had 12.5% of its carbon-14 left. How old exactly is that bone? Well, here's the first thinking. How many half-lives is 12.5%? So half-life 1 cuts it to 50%, half-life 2, 25%, half-life 3, 12.5%. And then I just take my 3 times 5,730, and I get my answer of exactly 17,190. Okay, and that's similar to what you've done with the flipping chips radiometric dating activity. Okay, now here it gets a little trickier. The igneous intrusion V, so if you look at this, this is an igneous intrusion where magma snuck up in. It was examined, and scientists found that it had 25% of its, of its uranium-235 remaining. What's the absolute age of the intrusion? Well, you have to be careful here. You can't multiply by 5,730. Check this out. Uranium's half-life is much, much longer. For half of the uranium-235 to convert to the stable form, it takes 713 million years. So here's our thinking. 25% left. Okay, how many half-lives is that? That's 2 half-lives. And so now we multiply by 713 million years, and you get an intrusion that is 1,426,000,000 years old. Another way to say that is 1.426 billion years. Now, our next question, our final two, asks, what do we know now about the ages of W, X, and Y? So we have to find them here on the diagram, W, X, and Y. We notice that the intrusion goes through those layers. So what does that make us think? Well, the layers had to be there first. They have to be older in order for the magma to sneak up in. So notice I've underlined the word older. All 3 of those layers must be older than the 1.426 billion years that we calculated. And then here's what you should say about the relative dating principle that you use. That's actually the principle of cross-cutting. Sometimes it's called cross-cutting relationships. And you don't have to have this part, but the idea behind that is what gets cut has to be older than whatever did the cutting. Oh, and I forgot we had this last one. Sorry about that. So number 5 here, why would a scientist ever pick potassium-40 over carbon-14 to find the age of a rock or fossil? Here are the words that you should have in those blanks. It has a long half-life, so it can be used to find the ages of rocks that are really old. Remember the idea that eventually at 50 to 60,000 years, carbon-14 will completely run out. It will be completely converted. And that doesn't mean that a scientist is just out of luck. It means they have to pick something else, like potassium-40, that has a much longer half-life to find the absolute age of things that are old. All right. That is it. Let me know if you have any questions.